Hello everyone, my name is Nikolai Promise Akura. Today I'm excited to present to you the Auto Rebalancing Hook for Uniswap v4 me and my team developed. This project leverages Uniswap v4 hook system to create smarter, more efficient liquidity pools that automatically adapt to market conditions. Let me show you how it works and why it matters in DeFi. Liquidity providers in DeFi faces several challenges, which range from capital inefficiency, impermanent loss. Our Auto Rebalancing Hook solves these problems by creating self-optimizing liquidity pools. Key features. The Auto Rebalancing Hook has three core capabilities, which are real-time market monitoring, automatic liquidity rebalancing, dynamic fee adjustment. Let's dive deeper into how each of these features work. The hook monitors market conditions through several key metrics, which are price volatility, trading volume, liquidity depth. This is how these metrics are calculated in our code. This update market function updates the market metrics for specific pools whenever market activities occurs, and it takes in two parameters, the pool ID and the swap amount. It retrieves the current state of a specific pool from storage, then calls getSlot0 function to get the current tick, right as the price level from Uniswap pool. It checks the volume tracking window. If it has elapsed, it resets the trading volume to 0 and updates the timestamp, creating a rolling window for volume tracking. If a swap occurs, swap amount is not 0, then it calculates the absolute value of the swap amount. Since swap can be positive or negative, it gets the absolute amount. Then it adds the amount to the current trading volume in the rolling window and also updates the total cumulative volume in the pool analytics. It calculates the change in price in ticks since the last update by finding the difference between the current tick and the last recorded tick. In getting price volatility update using EMA, we calculate the absolute change in price in ticks since last updated by finding the difference between the current tick and the last recorded tick. Then we'll convert the difference to an absolute value, which is a positive value. Then updates the price volatility using exponential moving average. Thus, if the first update EMA is 0, it sets the EMA to the current absolute change. Otherwise, it calls the calculate EMA function, which is a helper function in our code, to update the EMA with the new value. The EMA alpha determines how much weight is given to the value versus the historical value. Then the last tick is now updated with the current tick value. Let's look at another core feature's technical implementation. That's the liquidity rebalancing. The rebalancing mechanism works by determining the optimum range width. It calculates new tick range and moving liquidity from old range to new range when conditions change significantly. Here is how these metrics are calculated in our code. The calculate range width function determines the optimal range width of the price range for liquidity position based on market conditions. This takes in volatility and liquidity depth and returns the tick range. In situations where volatility is high or liquidity is low, it returns a maximum range width of 60 ticks. This is a defensive strategy to protect liquidity providers during extreme market conditions. If volatility is medium to high, it returns a medium range width of 30 ticks. And if volatility is medium to low, it returns a narrow range tick width of 20 ticks. For low volatility situations that is below 200, it returns a medium range width 5 ticks. This maximizes capital efficiency when prices are stable. This code snippet is for tick range calculation from rebalancing liquidity. This line of code here calculates half of the optimal range width to create a range centered around the current tick. And this code snippet, the lower tick is calculated by subtracting half range width from the current tick, whereas the upper tick is calculated by adding half the range width to the current tick. Both are adjusted using a get lower usable tick is a helper function to ensure they align with the pool tick spacing. For the upper tick, an additional tick spacing is added to ensure the range includes the upper boundary. Let's move to the third core feature technical implementation. That's the dynamic fee adjustments. Our dynamic fee system adjusts based on multiple factors. During high volatility, fee increases to protect LPs from impermanent loss. When trading volume is high but liquidity is low, fee increase to capture more value. In normal market conditions, fee returns to base level. Let me show you how the fee calculation works. The get dynamic fee function calculates the optimal fee tier based on current market condition. It takes in the pool key as input and returns fee value in basis points. It then retrieves the pool ID from the key and loads all relevant market metrics from the pool state. Fees are adjusted based on multiple factors. If volatility is very high, it returns the maximum fee of 1%. This protects LPs from impermanent loss during high volatility periods. And in a scenario where the trading volume is high and liquidity is very low, it returns the base fee plus 0.2%. Then in a case scenario where the trading volume is high, regardless of liquidity, it returns the base fee of 0.3 plus 0.1. Then in a scenario where the average price impact of the swap is high, that is greater than 2%, it returns the base fee plus 0.15%. And if the liquidity is low, below 200F, it returns the base fee plus 0.05. This slightly increases fee when liquidity is constrained. Then if none of the above conditions are met, it returns the base fee of 0.3. These functions work together to create a dynamic self-adjusting liquidity pool that monitors market conditions in real time, adjusts the price range width based on volatility, dynamically changes fees based on market conditions, and optimizes capital efficiency and returns for liquidity providers. Now let's see the hook in action with a demonstration of how it responds to different market scenarios. Under normal market conditions with low volatility, the hook sets a narrow price range for maximum capital efficiency, that's 10 ticks. It maintains the base fee of 0.3. During period of high trading volume but limited liquidity, fee adjusts upward to capture more value for LPs. The hook encourages small liquidity provision. The benefits of this hook are enormous since it creates value for multiple stakeholders. For the technical architecture, we have the core hook contract, position management, analytics module, feature improvements. While the current implementation is fully functional, we see several exciting directions for future development. Before I round up, let's look at the code. So this is the code base, and I won't be going through the code line by line since I've extracted the core features and explained it in the slide. So what I will basically do here is I'll run the test so that we can see what is happening, which I will do here. And I have 5 tests and all of them are passing. I tested for dynamic fee adjustments and it passed. I also tested for end-to-end workflow. I also tested for liquidity rebalancing here. I also tested for market condition monitoring. And lastly, I tested for position management. And you can see all my tests are passing. Thank you very much.